In this tutorial, I'm going to talk about some of the most important material properties that can be computed inside PuMA. Specifically, it will be focused on the thermal conductivity, both considering isotropic and anisotropic phases, and then also an example about the elasticity, which basically relies on a similar numerical method as the anisotropic thermal conductivity. So let me jump into the code and I will discuss while this is running. So first of all, I'm gonna import a sample of fiber form that is 200 cubed, as you can see up here. And then I'm just gonna, in this case, crop it so that it's 100 cubed instead. And this is just to show you how you would basically do this cropping operation. And then I'm rendering the contour of these cutoff values. So in this case, since I'm using the render contour, as you can see, I'm creating an isosurface that is triangulated along this grayscale range that I've decided. So I will close this and I will let the solver run through the function already. But then let me discuss about how you would basically assign the conductivities. So in PuMA, we have a class that is called Isotropic Conductivity Map. So for running the thermal conductivity function, considering the phases of our sample as isotropic, you basically call this and then add materials to it so that you specify the grayscale range and then add what isotropic conductivity you want for that specific phase. Then the second one is instead 12, which is basically for the fiber phase, since I'm selecting a higher grayscale range. And then it's basically just as easy as calling this compute thermal conductivity, feeding the workspace and the isotropic conductivity map. And then you would basically want to select the direction that you want to compute the effective thermal conductivity and assign the side boundary conditions. So in this, selecting a direction of X imposes a temperature gradient of 1 across the X phases. And so it keeps those as Dirichlet. And instead it keeps everything else as symmetric, since I put the side boundary conditions as S. You can select the iterative solver that you want. In this case, I put conjugate gradient. And then the solver has already completed actually, and the effective conductivity, which is basically the first row of the effective thermal conductivity tensor, has been output already. And finally in here, I'm just plotting the temperature and heat flux field that has been output as part of our function. So let me show you how the results look. In this case, I have the temperature on the left. So as you can see, along the x-axis, we have a temperature gradient going from 1 to 0. And then on the right instead, we have the heat flux. So not much heat flux, and this is mostly because the fibers are seem to be more oriented along the y-axis instead. But as you can see, the higher heat fluxes go for the fibers that do connect the X negative phase and the X positive phase. So pretty interesting. As you can see, the temperature follow how the fibers are arranged. So I will close this and I'll comment this first example considering isotropic phases. And now instead I will consider the phases as anisotropic. So I will again import the sample, and in this case, instead of cropping, I'm rescaling it, again just for showing you how you would do such an operation. So I will run this function again, and then something that is necessary for the anisotropic component is to compute the orientation of these fibers. So in this case, obviously, I'm basically assigning an isotropic phase to the air. This 0.0257 is the conductivity at room temperature for air. And instead, I'm giving the fibers a conductivity that is cylindrically orthotropic. So along the fibers, I'm giving it a conductivity of 12 and 0.8 instead across the fibers. So this is why we need the orientation. So as you can see, I'm actually outputting a rendering of the orientation that has been detected automatically using the structure tensor. So I will close this and let the solver solve for the effective thermal conductivity. And in this case, I'm computing it along the y direction, so it will be the second row of the effective tensor, and then again using symmetric boundary conditions. And in this case, since the MPFA, which is the numerical method that is used for computing the thermal conductivity for anisotropic phases, is more complex than the one that is used for isotropic phases, I need to use the big G stab, which is another iterative solver. So I will now let the solver converge, and then we will investigate together the results. Okay, the solver has now converged, and just FYI, I had to change, I had to rerun the solver so that this is correct. But let's investigate. In this case, this is the diagonal component, is the middle one, since we are on the second row of the tensor. And so here are our results for the temperature on the left and heat flux on the right. So as you can see, we have a temperature gradient along the y-axis. And so again, the temperature has converged to, basically follows the orientation of the fibers. And in this case, we have a very high flux for the fibers that connect from left to right this sample. So pretty interesting here. I will now close this one, and I will now run instead the elasticity one, which is a little longer. Comment the other one, and I will now rerun, close this one, and run the last example. So for the elasticity one, what I'm going to run is instead a sample of random spheres, and so in this case it's 100 cubed, and so I set also again the random seed so that the runs are repeatable. And in this case, I'm actually not treating the spheres to be solid, but I'm treating them to be the air phase, so everything else will be solid. And so as you can see, I'm binarizing this generated sample so that ID of 1 is given to the lower range. So in this case, what we get is basically a sample like this with spherical porosity instead. So one thing that is important for the elasticity is that there are no rigid body movements. So by rigid body movements, I mean basically floating unsupported voxels. Like for example, in this case, we could see these specific ones are just floating around without being supported. That would generate a singularity in our A matrix that we are solving for in the elasticity. So in this case, I've wrote a small function that is called remove RBMs, or rigid body movements. And so I will close this and let it run, and it will output re-render the removed RBMs sample. So as you can see up here, there are no floating voxels anymore. I will close this and let the solver run while I talk through it. So the first thing that we need to define is an elasticity map. So very similarly to the isotropic and anisotropic conductivity maps that we created earlier, what we want to assign now is instead the Young's modulus and the Poisson ratio for, in this case, for isotropic materials. We also have another option for passing an elasticity that has to be oriented with your phase in case it's orthotropic, or you can also give a complete anisotropic coefficient to this phase. So next we feed both the workspace and the elasticity map inside the compute elasticity, and in this case I'm giving a direction of x, so I'm computing the first row of the elasticity coefficient, and then using symmetric boundary conditions. And in this case it's yet again different. The iterative solver that I recommend is called GMRes. The reason for the different solver is because the numerical method that I use for the elasticity is based on the MPSA, which is called the multi-point stress approximation, and it's basically a level up in terms of complexity with respect to the multi-point flux approximation for the conductivity. So I will now let the solver solve for the elasticity, and what it will give us is basically U, S, and T are the displacement field, the sigma direct stresses, and the tau shear stresses for this specific setup. So in this case, since I'm running the x direction, I'm imposing a displacement of 1 on the positive x phase, and then that's kept as with Dirichlet boundary conditions, and instead I'm using a side symmetric boundary conditions. So briefly, these three fields are also going to be exported inside a VTI, which can then after be post-processed inside ParaView. But here I also prepared some plotting for showing the direct stresses, the shear stresses, and the displacement in several ways. So something that you can do is basically create just a PuMA workspace, and then fill in the orientation and the matrix as you can see down here, so that the render volume and the render orientation functions just work out of the box. I will let now the solver complete, and then we can take it from there. Okay, so the solver has now converged, and so as you can see, what it has given us is the first row of the 6x6 elasticity coefficient. So also the next part where I'm plotting it, I'm basically just building up. First, I'm rendering the orientation that is basically given by the displacement field. And so this is what I'm plotting in here, where I'm plotting a vector field. As you can see, you can barely see the porosity that is not rendered. So something else that I'm currently implementing is a function in PuMA to warp the domain, but it's not quite completed yet. So I would basically, for now, rendering it as a vector field, and you can see like what parts of the domain are basically displacing more than the rest. So if I then close this, and I'm gonna let the rendering generate the plot for the stresses, both direct and shear, and there they are. So as you can see on the top, I'm coloring the domain by the displacement in the x direction, and then the displacement in the y in the middle, and in the z on the right. And then the second row are all the direct stresses. So in the specific one that is interesting for this case is the x sigma direct stress, and as you can see, it's higher than the other two. And so finally on the bottom, you can barely see it, are the shear stresses. So some of the xz in this case, it's a little higher. So this completes the tutorial about the material properties, conductivity, and elasticity. Thank you for watching.